At some point long ago, you learned about exponents, where the exponents are positive integers. So 2 to the third is 2 times itself 3 times. And you've also worked with exponential functions, whose domain is all real values. And these feel like they're connected to you. So this is just a generalization of that one. So for example, f of 3 is the same thing as 2 to the third power. And you know what that means intuitively. You know how to evaluate it. But because the domain of the exponential function is all real values, that means that you have to be able to make sense of what this expression equals for any real value x. So what would it mean to evaluate f of negative 3? I mean, obviously it's 2 to the negative third, but you can't apply your intuitive idea over here directly, because what would it even mean to multiply 2 by itself a negative number of times? Or what would it mean to multiply 2 by itself a fractional number of times? You might have memorized at some point, or someone told you that this is the same thing as the square root of x, but that doesn't really explain very much. Like, why would it make sense that this should be the square root of x? And how does that idea connect to this idea over here? Like, is it just some random math fact, or is there some kind of connection there? So that's what this video is going to be about. It's about taking your intuitive definition of what it means to be an exponent when the exponents are positive integers, and we're going to extend the definition to apply to broader number classes, but in a way that's going to preserve the meaning of exponentials. Okay, well, so let's start with what we know here. You could imagine a data table for the exponential function 2 to the x with familiar natural numbers here. And the clear pattern is each time the exponent goes up by 1, that means take the previous value and multiply it by 2. Or if you wanted to think about it the other way, if you're going to start with a larger exponent and you want to make the exponent smaller, going this way, we'd take this value and you'd divide it by 2. Here you'd divide it by 2. And that lets us extend the table upwards. So this is 2 to the 1. If I wanted to define 2 to the 0, that would be like asking what value times 2 is going to give me 2. And you know the answer is 1. But you could equally well think about it the other way. If you're thinking about dividing by 2, then 4 divided by 2 gives you 2, 2 divided by 2 gives you 1. And you can keep extending the table upwards. So let's do that. So clearly, the same pattern has been preserved. So if 2 to the negative 3 is 1 divided by 2 times 2 times 2, if I multiply that by 2, I should end up getting 2 to the negative 2. And indeed you do, because one of the 2's cancels. So you can see that this way of extending it has preserved the overall pattern, but it also gives us a way of interpreting what negative exponents mean. You can see here that the negative exponent 3 is the same as the reciprocal of the exponent if it were positive. So 2 to the negative 3 is 1 over 8, and that's the same thing as 1 over 2 to the third, 8. So if you were going to generalize this, so you can see this kind of symmetry in the table, and you could generalize this to a general identity. You know that 2 to the n equals 1 over 2 to the, 2 to the negative n equals 1 over 2 to the n for values of n that are integers. Okay, was this a proof? Did I prove that this is true? No. This is a definition. I'm defining what does it mean to be a negative integer exponent. But it's a motivated definition. It's motivated by our desire to have exponents all follow the same pattern, because that's going to make all of our mathematics work out more generally and more nicely. So, for example, you can do some basic arithmetic with positive integer exponents just based on your intuitive definition. So if 2 to the third is 2 times itself 3 times, and you multiply that by 2 times itself 4 times, so this is 3 2's, and that's 4 2's, so that gives us 7 2's. So when I multiply this by that, that's the same as 2 times itself 7 times. So if I wanted to generalize this, 2 to the a times 2 to the b should be equal to 2 to the a plus b. And it's like very visually clear why that should be true as long as a and b are positive integers. Because when they're positive integers, we can write it this way and it all makes sense. So I just finished saying that our definition for what it means to be a negative integer exponent is a motivated definition, and it's motivated by our desire for negative exponents to follow the same patterns as positive exponents. And this is one of those patterns. So go ahead and try it for yourself. Let's see if a and b are negative integer exponents, if this rule still holds true. So go ahead and write out 2 to the negative 3 times 2 to the negative 4. Whoops. According to our definition, so you can write out what these should be equal to using our definition, and then you can verify whether or not this rule actually still applies. So is it actually still true that this equals 2 to the negative 7? Go ahead, give it a try. All right, so if I apply my definition of what 2 to the negative 3 means, it's the reciprocal of 2 to the third, so there we are. This is the reciprocal of 2 to the fourth, so there we are. And you can see that this is the same thing as 1 over, and then there's 7 2. Okay, there we go. So that's the same as 1 over 7 2s. And then applying again the definition, that's the same thing as 2 to the negative 7th. So we've sort of verified that according to our definition, this rule still holds. So armed with this idea that we want to extend the definition for exponents, keeping these rules true, we can think about what should make sense for 2 to the 1/2. So if a is 1/2 and b is 1/2, and we want this rule to remain true, it should be true that whatever number this is, we should have like mystery number times mystery number equals 2 to the 1/2 plus 1/2 is 1 equals 2. So if we think about that, now it makes a lot of sense why 2 to the 1/2 should equal the square root of 2, because root 2 is the unique number defined as the number when multiplied by itself that gives you 2. Similarly, if we had 2 to the 1/3, for example, 2 to the 1/3 times itself, according to this rule, should be 2 to the 2/3. If I take that and I multiply it by 2 to the 1/3, again, using the rule, that should equal 1. So put that all together, and we've got 2 to the 1/3 times itself 3 times should equal 1. And again, if we call this mystery number, we've got mystery times mystery times mystery equals 1. Equals 2 to the 1. So that's the same thing as writing like x cubed equals 2. So x should be cube root of 2. So we can generalize that to a new definition. 2 to the 1 over n should be the nth root of 2. And of course, this is not general because I'm using 2 here. We could have k, and then up here we could have k and k. All right, so where are we so far? So we started off with an intuitive idea of what positive integer exponents mean. We extended that definition for negative integer exponents. Now we have exponents that are of the form 1 divided by a positive integer. We're not quite up to rational exponents, so what it means to be like a over b. So for example, 2 to the 3/2. But all of these definitions were created to satisfy this rule that we think should be true. So let's try and figure out what other things do we think should be true based on our understanding of positive integer exponents. So let's think about 2 to the 3 to the power of 4. What this is literally saying, so on the inside here, 2 to the 3 means 2 times itself 3 times. And then that's being raised to the 4th power, which means this. So we've got 2 times itself 3 times, and we've got that 4 times. And so clearly this is the same as 2 to the 12th. And so if we're going to generalize this, you can see that if we've got 2 to the a and then raise that to the b power, then here I'll have 2 times itself a times, and then those a repetitions of 2 are being repeated b times. So if this is a times, a times, a times, a times, and then this is b a's, that's the same thing as a times b. And notice we could group these differently. So here we had 3 2's grouped into 4 groups. If we change the parentheses, you can also look at 2 to the 12th as 3 groups of 4, like this. And so what that also shows us is 2 to the a to the power of b can also be written as 2 to the b to the power of a, because it's just changing your thinking about how big each group is compared to the number of repetitions of each group. So this gives us another identity. Now we've got 2. We know what it means to multiply 2 numbers with the same base, where you have positive integer exponents. And we know what it means to raise one of these to a power. I'll leave it to you in the exercises to verify that our definition, that these other extended definitions that aren't positive integers also satisfy this new rule. But if this new rule is true, it gives us a really nice way of understanding what a rational exponent would mean. 2 to the 3 over 2 you could rewrite as 2 to the 1/2 to the power of 3. Or you could rewrite it as 2 cubed to the power 1/2. And then if you're going to apply the definition of 2 to the 1/2, that would give you root 2 cubed, or that would give us square root 8. So we can codify that over here. K to the a over b, where a and b are integers, gives us bth root of k raised to the a power. So to sum up, we have these two identities, which are just descriptions of things that are like completely obvious if a and b are positive integers. And they're completely obvious just based on our intuitive understanding of a positive integer exponent being the base times itself that number of times. But then we decided to extend the definition of exponents to include not just positive integers, but negative integers and also rational numbers. And we chose to define them in such a way that it would keep those two identities true. And there were the definitions that we chose to make. So you can use these. These are immensely useful in simplifying algebraic expressions that involve roots of any kind or that involve exponents of any kind. And you'll see that because logarithms are the inverse of exponents, each of these rules here has a parallel identity for logarithms.